the Castellian-Myers high mass and low mass relationships do not lie very well within our distribution of sources. The last thing we did was we ran some Monte Carlo simulations, because now that we can compute source parameters, now that we have distances, we can compute source parameters. So what we did was say, okay, if we assume a temperature and then sort of a sigma t, a temperature distribution, how does that change our results that we might find? Because in our paper we use basically a empirically derived temperature of about 20 Kelvin. And so we wanted to see, well, how much would we be off by changing our temperature distribution? The answer is about a factor of 2. Our median mass for our distribution, if we choose a high temperature, it would be about 200, whereas down here it's about 700. So depending on what you assume to be the properties of your clumps, you can change your result by a factor of 2 just by assuming a slightly different temperature or temperature distribution. And so that same factor goes in for median surface density, median number density, and then also the differential mass histogram slope. And so for this, we did a maximum likelihood analysis for the slope of the differential histogram, and you can see how it changes with temperature itself. So saltpeter on this scale would be 1.35. And in this case, in our area where we chose severe temperatures about 20, there isn't a whole lot of change. But depending on what temperatures you choose, you can push the slope that you find for your mass distribution around. Quickly, our clump crossing times and our free fall times are fairly well matched. Comparing some of the virial parameters, we also see that they're fairly well matched, and so we assume that many of these clumps are gravitationally bound and potentially collapsing. But with that, I will leave up my conclusions, and I can take any questions that you may have.
James.
Thanks. I'm sorry, I might have missed this, but how did you determine the size for your line width size relation?
Okay, so with the sizes, we go back to this sort of thing right here, where each one of these ellipses has a size. And so we fit the source size from the BGPS maps, not from a... So we're comparing, I guess, that would be dust size versus HCO plus line width.
And is the size of the beam comparable to the size of the clump?
Almost every single one of our clumps are resolved, so they are larger than the beam size. And Kara Battersby at Colorado has done mapping of some in IRDCs, but of BGPS sources, and finds that the gas and the dust are well coupled.
More questions for Wayne at the back?
You mentioned the Pareto and Fuller infrared dark cloud survey and some kind of correlation that you did to use that in disambiguating the distances, but I didn't quite understand what you said you did with that. Could you just explain that again?
Okay, so let's say that there was an IRDC right here. If one of our sources was within that ellipse, we would say that it was probably associated with that infrared dark cloud. And then in additional to just saying, okay, well, it's associated within a mathematical ellipse, we compared the location of our sources to the Spitzer images themselves to say, well, okay, does our source look like it actually lies, correspond to that dark cloud? And so we vetted that list by eye to have association. And then if they were still associated, we said that it was at the near distance.
One other question at the back there.
I'm just wondering whether the coverage of BGPS overlap in any way with the galactic width or protein field.
It does. It does.
So, so it's like, for example, if you look at llamas from HCO class, is it different from the without
Different.
I say if we just using the velocity.
So our velocities do correspond with with peak velocities that are in the CO from the GRS. It's just the difference is that with CO, because there's so much of it, you can see it all the way across the galaxy at many different velocity components, whereas ours typically correspond to the densest gas, which is also going to correspond most likely with the BGPS clump that we're being observed.
Al?
Densest gas, so you've got the 1 millimeter fluxes and sizes of these, so you must know a mean density for the dust, and then how does that compare with the excitation density for the lines that you observe? What densities are we talking about?
I have to think about that. So the densities, the gas densities themselves are on the order of like 1 to 2,000 per cubic centimeter, and I have to think about. I don't remember the dust densities off the top of my head, but they both have very similar effective densities, so they should be comparable to each other.
Okay, one more question for Wayne. If not, let's thank Wayne again, and especially for dealing with faulty equipment. Thank you.